All right, so in this chapter, we'll learn about a new quantity called momentum. Okay? Now, whenever we introduce a new concept, it obviously is helpful. Okay, so you'll see that in certain situations, momentum will be very useful. Okay, so let's see that. And again, like the chapter title says, in collisions, the idea of momentum will be very useful when you want to analyze collisions. Okay. All right. Now the title says linear momentum. Okay. In a couple of chapters, we'll also define something called the angular momentum. Okay. So right now, we'll talk about linear momentum in this chapter. All right, so in this chapter, we'll define another conserved quantity. Okay. What does this expression mean, conserved quantity?
No energy is lost to the heat.
Okay, so conserved quantity, just like energy, okay, so for an isolated system,
No momentum is lost.
energy is constant, and you will learn that momentum denoted by P is also constant. Okay. Now here's how you think about it. So let's say, I'll give you a financial example. So this is a constraint. What that means is, let's say you have $100 to spend over a month. Okay. Now, if that's a constraint, there's only so many ways, so many things you can do with $100. Okay. And then on top of that, let's say you have to spend your money within a couple of blocks. Okay. So the more and more constraints you put on a system, the less and less freedom you have. Okay. So for an isolated system, you will learn that the energy will be constant. Okay. And the momentum is also constant. Okay. So that's what we mean. So in this chapter, we define another conserved quantity, linear momentum, which will put an additional constraint on how a system can evolve in time. Okay. So how many different configurations the system can take is constrained by these two things. All right. Anyway, those are a bunch of words that you'll understand later down the road. But conservation of momentum is useful for understanding collisions. Okay. So what you'll learn is when two objects collide, the total momentum before the collision will equal the total momentum after the collision. Okay. Whether or not mechanical energy is conserved or not, momentum will always be conserved. Okay. So that's what you'll learn. So the quantity momentum is just as powerful, important, and useful as energy. Okay. Again, why do we define new and new quantities? Because they're useful, and when the old quantities that you have defined are not sufficient to analyze new situations. Okay. Anyway, so momentum is a useful quantity. So if you want to analyze situations like this, okay, so when the bat hits the ball is exerting a force on the ball. So the bat is exerting a force on the ball. Okay, so let's say, and this force is changing with time, and this force might exist for, let's say, about 50 milliseconds. Okay, the force that the bat exerts on the ball. Okay, so in situations like this, linear momentum is very useful. Okay, and you can't solve this using force equal to mass times acceleration and so on. Okay, so that becomes difficult. So often we encounter situations where the applied force varies with time and is non-zero for extremely short intervals. Okay. So this force, for instance, is varying with time, and it's alive for only about 50 milliseconds. So if you plot a force versus time like that, the force will be like something like this, and this will be about 50 milliseconds. Okay. Of course, if the ball is softer, for instance, tennis balls, the collision might last longer. Soccer, the collision lasts longer. But for a hard ball, the collision is very short. Okay? So to analyze such situations, we define momentum. Okay? So momentum, linear momentum is denoted by P. And what does that arrow tell you? It's a vector quantity. Okay? So linear momentum is mass, a scalar, times velocity, which is a vector. And that's a vector. Okay? So linear momentum is a vector quantity, and it's equal to that. Okay? Now, we introduced Newton's second law for you guys before. What is Newton's second law? Do you guys remember? What was Newton's second law?
The time rate of change of linear momentum.
Yeah.
To the net force.
Well, you're reading that one. Okay. So we defined Newton's second law as net force was equal to mass times acceleration. Now, this is a special case. Okay. Now, let me tell you what it means. Okay, so the correct form of Newton's second law is that. Okay, is the net force acting on a system is the time rate of change of the momentum of the system. Okay. So now let's look at this. Okay. Why is this a special case? So let's look at this equation. You guys are all experts in calculus. So let's use that knowledge. What is momentum? Momentum is mass times velocity. Okay, so let's put that in here. Mass times velocity. And I'll be a little explicit. So mass as a function of time times velocity as a function of time. All right, so now we'll use the chain rule on this. It's d by dt of mass times velocity plus mass times dv by dt. What is the time rate of change of velocity? What is that? What is dv by dt? Acceleration. Okay. Yeah. And and there is this term, dm by dt times velocity. All right, so we told you that Newton's second law was force was equal to mass times acceleration. So the force acting on a system is mass times acceleration plus this term. Okay, and we never mentioned this term. Why didn't we mention this term? Yep.
So because mass is always constant.
Yes, so in most of the situations, mass is always constant and this is zero. And so then in most cases that you encounter, force is mass times acceleration. Well, is there any situation where the mass is not constant?
In a collision where something breaks off.
So if you're Elon Musk and launching rockets, your mass changes quite a bit. For a rocket, 90% of the mass is fuel, and you lose that mass within a matter of minutes. Okay, in 5 minutes you're in orbit. Okay, so there are situations where the mass changes tremendously, and this can be larger than that term. Okay, then this is non-negligible. Okay, when you're driving a car, does the mass of your car change? Yeah, it changes, but it changes very little. So in that case, when you're driving your car, you can ignore this term. Okay, but there are situations when you cannot ignore this term. Okay, and we'll be interested in that kind of stuff. All right, so this is the most general form of Newton's second law. This is a special case. And when does that apply? That applies when the mass of the object doesn't change significantly, okay, or not at all. All right, so here's Newton's second law. Okay, so in terms of linear momentum. All right, this also, so now the correct form of Newton's second law tells you the force you need to apply to change the momentum of an object by that much in this time, okay? So if you want to change the momentum faster, then you have to apply a greater force, okay? So for instance, here are some objects. Here are some objects whose momenta are given in SI units. So here's an alpha particle that is emitted by U-238 when it decays, and there's the momentum of the alpha particle. An alpha particle is a helium nucleus. Okay. Here is the momentum of a 90 mile per hour fastball, about 10 kilogram meters per second. Here's a charging rhinoceros, and its momentum is 3 times 10 to the 4 kg meters per second. Okay, so for instance, what does this number mean? Why are we giving you these numbers? So force is change in momentum divided by change in time. Okay. So now let's say you want to stop this rhino. Okay. And you want to stop him in 1 second. Okay. So how much the momentum you need to change is that much. Okay. And that is 3 times, okay, now I'm going to write 30 times 100, 1,000 kg meters second per second. If you want to change him that much, this is newtons. That's 1,000 newtons is roughly the weight of 1.5 person. So the force you have to apply is equal to the weight of 45 people. That's what that means. Okay? So you want to stop a charging rhino, 45 people need to stand there and push all at the same time. Okay? So again, anyway, this tells you if you want this much change in momentum in that time, that's the force you need to apply. Okay? And obviously stopping a supertanker is a little harder. Okay? All right. In your life, you have many safety devices. And what do the safety devices do? Okay, so here's, so, all right, this is the force acting on you. Okay. And if you're trying to change the momentum by that much, if you change this momentum over a longer time period, if this is larger, then the force on you is smaller. Okay. So what you want is a smaller force acting on you, and that's the job of safety devices. Okay. And you do that by changing that momentum over a larger period of time. So for instance, here's a dummy in a car, and let's say the car is going at 80 miles an hour in that direction. Okay. What is the speed of the dummy? Also 80 miles an hour. Okay. And let's say the car gets stopped by a tree or something like that. And if the car gets stopped, the dummy will still be moving at 80 miles an hour. And if the steering wheel happens to stop the dummy, that'll be a very fast stop. Time delta t will be small, and the forces on the dummy will be greater. And then there's the additional concept of greater pressure, but we won't worry about that right now. Okay, so how do we make this time larger? You deploy an airbag, and the dummy gets stopped over a larger time, thereby exerting a smaller force on the dummy. Also, the force is spread over a larger area rather than a small area, and so the pressures are smaller as well. Okay. Now here's an interesting thing about an airbag that you guys probably already know. So let's say the tree stopped the car and the dummy is starting to move. So you see that the airbag has to be deployed before the dummy gets to the airbag. Okay? So this airbag actually blows up at about 200 miles an hour. So you guys know that you don't want to be driving a car by being too close to the steering wheel. What would happen? I mean, you get into a wreck, the deploying airbag will do you damage, and then there'll be more damage down the road. Okay? So you don't want to be too close to the steering wheel. Anyway, safety devices are you're changing your momentum over a larger time period, so the forces acting on you are smaller. Okay? And that's the goal. All right, now we'll consider situations where the concept of momentum is very useful. So here's a situation that you encounter in life. Okay, so let's say, so we're looking at the instance for the time period when the club is in contact with the ball. Okay, and the force that the club exerts on the ball, okay, is changing with time rapidly, and it's exists for a very short time, about 50 milliseconds. Okay? And what the impulse approximation says is the following. Okay. Okay. Now this force in practice can be as large as 3,000 times the weight of the ball. Okay. So now let's look at the forces acting on the ball during this time period for this short amount of time. Okay. So let's see, what are the forces acting on the ball? Here's the force that the club exerts. Here's the force of gravity. And is there any other force? There's the normal force and there's friction force. Okay. Now for this short amount of time, all these forces are negligible compared to this force, this large force. Okay? And you can ignore them. By the way, the normal force is being canceled by the gravity anyway. Gravity is being canceled by that. So the other non-zero forces, well, the other force is friction, and you can neglect friction compared to this force. Okay, so that's the impulse approximation. You can ignore all other forces while this large force is acting. Okay. And now let's see what is the effect of this large force on the object on which the force is acting. Okay. Now what is the property of this force? Well, the force is changing and it exists for a very short time. Okay. So now let's see how to analyze the effect of this force. All right. When you're playing golf, let's say, what are you interested in? So the golf ball was at rest, and all you care about is at what speed the ball comes off the tee. Do you want to know the change in speed of the ball? No, and you can't track that. Okay. So what was the initial speed of the ball? 0. And what you're interested in is what is the final speed of the ball? Okay. After it's come off the club. Okay. So all right, so now let's analyze that. So impulse and momentum. So here's Newton's second law. Newton's second law says this is the force acting on the ball, and what is exerting the force?
Club.
The club. The force exerted by the T, gravity, and friction are being ignored. Okay, so this is just the force exerted by the club, and that's equal to rate of change of momentum of the ball. Okay, now this force, the force exerted by the club, varies with time like that. Again, this is a vector equation. Okay, so force is a vector and dp by dt is a vector. Okay, for now we will dispense with the vector signs. We'll consider a one-dimensional case. So the force is in that direction and the ball is going to fly off in that direction. Okay, what we're going to do is so the slide has all the vector notation, but let me do this without a vector notation. Okay. So there's the equation. What we're going to do is hit the left-hand side with a hammer, and we're going to hit the right-hand side with the same hammer. Okay? And okay, since this force exists only between these two times, we'll integrate between those two times. Okay. What are those two times? What is that time? What happened at that time?
When the club touches the ball. To
When the
ball hits
club
the
came in contact with the ball. And this is when the ball came off the club. Okay? So those are the time intervals. And what is this guy? What is this guy?
The net force that was
No. What is that guy? That is the area under that curve. Okay? So this area is called the impulse. And some textbooks denote it by I and J. Okay? So this guy is the area, J. Okay? And what is this guy? Okay, that's a time derivative, and that's an integral. What does the integral? It undoes the time derivative. And also from the fundamental theorem of calculus, you know that that is Pt. Okay. So that's the final momentum minus the initial momentum. Okay. So what did this tell you? Okay, so what was the initial momentum of the golf ball? What was the initial momentum of the golf ball? Zero. Its initial velocity was 0. Okay? And what is the final momentum? mv final minus mv initial. Okay? So you see this was 0, and the left-hand side is the impulse. That is the area under the curve tells you how fast the ball will come off the tee. Okay? So if you want to earn millions and millions of dollars, all you have to do is increase the area under that curve. Okay? So the difference in area between a professional golfer and me is probably a factor of 2 or 3. All right, so here is a situation where momentum is very useful. Okay, so this is called the impulse momentum theorem. Okay, so the impulse imparted by the club shows up as change in momentum of the ball. Okay, and this is the impulse momentum theorem. Okay, did you guys understand that? So in situations where you're applying a time varying force, and that the force is changing rapidly and is active for a very short time, this momentum is a very useful concept. Okay, so the impulse imparted in the object is equal to the change in momentum of the object. Now, in lab, we'll do an experiment where we'll actually measure this force. Okay. And that'll be the best experiment you do this semester. You'll measure the force 500 times a second. Okay. So we'll measure that, and then we'll measure the change in momentum of the object on which that force is acting. Okay. Now, oftentimes you're not able to measure this force, so all you're interested in is the area under the curve. Okay. The area under the curve will tell you the change in momentum of the object on which the force is acting. Okay. So oftentimes what you do is all you ask for is what is the average force acting on the object. Now the average force is defined by average force times time. This area is equal to that area. That's how average force is defined. Okay? So the impulse is equal to the average force times the time over which it's acting. Okay? And oftentimes we are happy with that. Okay? All right, so now let's introduce the idea of conservation of linear momentum. Okay, so let's say you just saw this. What is Newton's second law? The correct form of Newton's second law?
force net equals the change in momentum with the change in time.
All right. So the net force acting on an on a system, on an object is equal to dp by dt, the rate of change of momentum of the object. And you'll see soon that this can be applied to a system as well. Now here's the simple idea. If this was 0, if the net force acting on a system is 0, then dp by dt is 0. What does that mean? I'm sorry? Yep, so this is constant. Okay, so imagine a system where a whole bunch of collisions are happening, but the net force on the system is 0. The total momentum of the system will be 0. Okay? So let me show you a little video for that. Okay.
Look at that. Is that not the most pretty break?
Okay, so what I want you to pay attention is, okay, after he hits the cue ball, okay, now, okay, so after he hits the cue ball, okay, so here's the rack. I'm sorry? It's a little slow, so here's the rack. Once he hits the cue ball, now what is the total momentum of this system? What is the total momentum of this system? It's just the momentum of the cue ball, right? Okay. And then the cue ball will hit this thing, the rack, and all these balls will scatter. And the total momentum of the system, the net force acting on this is 0, because the force of gravity, if you look at it sideways, the force of gravity is being canceled by the normal force. There's no friction force, essentially. Okay? The net force on the system is 0. So after the rack is broken, the total momentum of all the balls will equal the initial momentum of this guy. Okay? So you can make a statement like that. Till when will that be true? I'm sorry?
Hit the wall.
Till the first ball hits the side. Okay? And if there were no sides, then the total momentum would remain constant forever. Okay? All right, so it doesn't matter how you break the rack. Okay? So you can make that statement, the initial momentum will equal the final momentum. Okay. So that's a pretty powerful statement. And of course,
That right there is how you're supposed to rack the ball. Look at that. Is that not the most pretty break? That right there is how you're supposed to rack the ball.
all right, so now you've learned something that you can say about this game. Okay. All right. All right, so what is conservation of linear momentum? If the net force acting on a system is 0, then the momentum of the system does not change. Okay. By the way, the net force acting on a system is internal forces. Oh, come on. Are you going to? Did you come on? Nope. No? All right, everybody watch that slide. All right. So, again, the net force is internal forces times external, plus external forces. Okay, so what are internal forces? Let's say, well, when this guy is in contact with him, each ball will exert a force in opposite direction. And what does Mr. Newton say? These forces are equal and opposite. So internal forces always cancel each other. Okay, so these will add up to 0. So if you add these two forces. And so the net force acting on a system is just the external force. And if the external force acting on the system is 0, then the momentum of the system will remain constant. Okay, and that's what you saw in that pool simulation. Okay, so momentum, the total momentum before the collision is equal to total momentum after the collision. Yeah, and so this is kind of the law that people use in accident reconstruction and stuff like that. When people analyze accidents, this is the law they use. Okay. So again, a very powerful concept. Okay, so here's another situation that particle physicists use all the time. Okay. In analyzing situations in colliders and stuff like that. Let's say you make a particle, this particle, and this will decay. It breaks up into these two particles. The kaon decays into these two pions. And now, so the decay forces are internal forces. So if the initial momentum, so if this was at rest, the initial momentum is 0. And so the final momentum has to be 0. And what does that mean? Okay, so these are particle antiparticles. They have the same mass. Okay, how can the final momentum be 0?
They're going in opposite directions.
Well, and
their masses and speeds are
exactly. So not only they have to fly apart 180 degrees apart, and their speeds have to be exactly the same. Okay, so those are the kind of statements you can make. Okay. All right, so linear momentum is useful concepts when we study collisions. So now let's study collisions in a little more detail. Okay, we'll introduce a little terminology. Okay. What is kinetic energy? That's being noisy. All right, what is kinetic energy? Kinetic energy is the energy of motion, okay? So kinetic energy is 1/2 mv squared. Okay, now this is not conserved in collisions, okay? Kinetic energy can be converted to other kinds of energy, heat, sound, and stuff like that, and so on, okay? So it'll turn out that this is not very important, but we'll use that to define some terms. Okay, if the kinetic energy after the collision is equal to kinetic energy before collision, then it's called an elastic collision. If final kinetic energy is less than initial kinetic energy, that's inelastic collision. Well, what happened to the kinetic energy? It just got converted to other forms of energy. Remember, energy cannot be destroyed. It just got converted to, let's say if part of it got converted to heat, that's very hard to keep track of, okay? So it just gets converted to other forms of energy. If the final kinetic energy is 0, then some authors call that a perfectly inelastic collision. Can you think of a situation where that might happen?
cue ball hitting
No.
throwing a stupid piece of putty at a wall.
Yep, okay. So you take 2 pizza balls and throw them at each other, and they'll stick, and and they won't go anywhere. Okay. So that will be a perfectly inelastic collision. And if kinetic energy, final kinetic energy is greater than initial kinetic energy, then that event is an explosion. Okay. So that's what happened. All right, so we just introduced terms using kinetic energy. Okay. Now, so here are a variety of collisions where kinetic energy is either conserved or not conserved. But what you learn is in all these guys, momentum is conserved. So you see, momentum is a more fundamental quantity in collisions than kinetic energy. Okay. So energy, of course, total energy, of course, is always conserved. But momentum is very useful in analyzing collisions. Okay. So no matter what kind of collision you have, momentum is always conserved. What does this mean? Momentum after the collision is equal to momentum of the system before the collision. Okay. And that's what we're going to use. Okay. So here are two objects colliding. First, we'll consider the simple situation of a 1D collision. What do we mean by a 1D collision? Right, so everything, the objects are moving in a straight line before the collision, and they're moving in the same straight line after the collision. Okay. So we'll consider, okay, so here are two objects colliding, and after the collision, let's say they stick together and they move like that. What did we just learn? Well, since there's no external force acting on the system, momentum, total momentum before the collision will equal total momentum after the collision. Okay? And what that does is it puts a constraint on the velocity. If they stick together, they have to be going at a specific velocity. Okay? So that's, all right, so what is an elastic collision? An elastic, in all collisions, momentum is always conserved. Okay? Momentum is always conserved. In an elastic collision, kinetic energy is also conserved. Okay? In an inelastic collision, kinetic energy is not conserved. Okay? And so most real life, most macroscopic collisions are inelastic collisions. The cue balls happen to be an elastic collision. Okay, but that's how they're built. Okay, so when two cars collide, for instance, it's an inelastic collision. Now at a microscopic level, so in this room, there's billions and billions of air molecules colliding. All those are almost always elastic collisions. Okay. But when macroscopic objects collide, like a baseball bat hitting a ball, that's an inelastic collision. Okay. Yeah. So on. All right. So in an elastic collision, kinetic energy and momentum are conserved. In an inelastic collision, only momentum is conserved. You see, momentum is always conserved. Whether other quantities are conserved or not, that's a different matter. Okay. So let's look at first an inelastic collision in one dimension. Okay. So these two guys collide, they stick together, and they go off with a final velocity. And since momentum must be conserved, here's the momentum before they collide, initial momentum, and there's the total momentum after they collide. Okay? So the final velocity has to have this specific value, initial momentum divided by the total mass. Okay? Now we'll look at an elastic collision in one dimension. What does an elastic collision mean? Okay. And what else is conserved? Yeah, so momentum is conserved, and in addition, kinetic energy is also conserved. Okay. So momentum is always conserved. Okay, so here's momentum before the collision. These are initial values, and there is the momentum after the collision. So momentum of particle 1 plus momentum of particle 2. Okay, so here they are colliding. Okay. And momentum is conserved, and since kinetic energy is also conserved, this must equal that. Okay. And of course, so this is two equations, and so you can solve problems involving two unknowns. Okay. It turns out that if you do a little algebra, you can manipulate these two equations into these two equations. Okay, this equation is the same as that equation. Okay, except this equation is slightly different. Well, what is this equation saying? V1 initial minus V2 initial. Okay, so here's V1 initial. So if this is, let's say, if this is 5 meters per second, and this is minus 7 meters per second. What is V1 minus V2 initial equal to? 5 minus of minus 7. That gives you 12 meters per second. What is that? That is the relative velocity of the two. So if you were sitting on this ball, 12 meters per second will be the speed at which this guy is coming at you. Or if you were sitting on this guy, 12 meters per second is the speed at which this guy is coming at you. Okay? So this is the relative velocity. And so what is this equation telling you? For an elastic collision in one dimension, the relative velocity before the collision is equal to the relative velocity after the collision, except with a negative sign. Okay? So what that is saying is, if you are watching the collision sitting on this guy, is this guy is coming at 12 meters per second at you. After the collision, he'll go away at 12 meters per second. Okay? Or if you're sitting on this guy is coming at you at 12 meters per second. After the collision, this guy flies off at 12 meters per second. Okay, so that's what that equation is telling you. Okay? And this is true only for elastic collisions in one dimension. All right, so if you encounter a problem with that, you want to use these two equations rather than these two equations. Okay. Why do you want to use these two equations rather than these two equations?
Say that again?
Why do you want to use these two equations rather than these two equations? And this is true only for elastic collisions in one dimension. The information content is the same.
Well, they're simple.
Huh?
They're simple.
Why are they simpler?
So now V squared.
Yep. So this is a quadratic equation in velocity. This is a linear equation in velocity, and that's why they're easier to solve. Okay. All right. So here is a 2D. Now we'll graduate to 2D collisions. Okay. So here's two objects colliding. Okay, and now we give them the freedom of moving in two dimensions, and this guy, after collision, goes off in this direction, this guy goes off in this direction. Okay. Now again, in this collision, momentum must be conserved. Okay. Except that momentum is, in this case, now we have two dimensions. So what that means is, what this means is P initial x should equal P final x. Each component must be conserved. Okay. So since this is a vector equation, okay, the x component initially should equal the final x component, and initial y component should equal final y component. Okay, so let's look at this guy. Okay, the initial total momentum is only in the x direction. Okay, so when after they collide, they go off like that. The y component of the momenta should cancel, and the x component should add up to give you the initial x component. Okay. So that should be true. Okay, so here is the initial x component of the momenta, and that should equal the final x component of the momenta. Initial y component of the momentum for the system should equal the final y component of the momentum. Okay. And in addition, if the collision is elastic, then this should be true. Initial kinetic energy should equal final kinetic energy. Okay. So here's a situation where you have three equations. Okay. So for a 2D elastic collision, 3 equations must be satisfied. Okay? Now, it turns out that if the masses are equal in 2 dimensions, they will always fly off at 90 degrees. Okay? Did you guys know that?
I did not.
Huh? Yes, you knew that. Do you play pool?
I didn't know that.
Yeah, but you subconsciously knew that because that's what you were using when you were playing pool. Okay. So if you want to, when is that true? Just made a statement. When is that true? When the masses are equal. So the cue ball mass is equal to the object balls. So if you want to beat somebody at pool, have a cue ball in your pocket which has a different mass. And so you can beat a world champion as well. Okay? Well, you got to be slightly good. But if you put a cue ball that is slightly different mass, or a lot different, you can beat. All right, now we'll define something called the center of mass. Okay, so let's say I toss a ball. What is the trajectory of the ball? So here I'm tossing this keychain. What is the trajectory of this keychain? I toss a ball. The trajectory is the parabola. Okay. Now you see, this guy is tossing a baseball bat, and there's only one point in the baseball that goes on a parabolic trajectory. Every other point is not going on a non-parabolic trajectory. Okay, that's a non-parabolic trajectory. And the point that goes on a parabolic trajectory is called the center of mass of the object. Okay, so if you were to make the baseball, if you were to crush the baseball bat into a point, that's where you would crush it into. Okay? So that's the center of mass. The center of mass is the only guy that goes on a parabolic trajectory. So the center of mass of a system of particles is the point that moves as though the entire mass of the system were concentrated at that point. When an extended object is tossed in a constant gravitational field, the center of mass travels on a parabolic trajectory. Okay? So if you wanted to find the center of mass of any object, what you can do is you can suspend it by one point. The center of mass will be below that point of suspension, somewhere on that line, and then suspend it from another point, and the center of mass will be like that, and the intersection of those two lines will be the center of mass. Yep. So that's how you can find the center of mass of any object. Now the center of mass of a bunch of point objects, the center of mass doesn't need to be within any object. So here is the center of mass of this system. So if this were the solar system, there is the center of mass. Okay? So here is a neat thing, for instance. What does the Earth go around?
The sun.
The Earth goes around the sun. Again, so that's what any smart person would say.
Well, the center of mass of the two.
That's right.
Which is slightly deviated from the center of the sun.
Right. So there is the center of the sun, there is the center of the Earth. The center of mass of the Earth-Sun system is there, assuming only two objects in the. So the sun goes around this center, and the Earth is also going around that center. Okay, so that they're orbiting about the common center of mass. Okay, and that's roughly about 300 kilometers or so. Okay. So now let's just look at the sun. The sun is going around in a circle. Okay, so if you're here, okay, when the sun is going like that, you guys know about the Doppler effect. when a siren comes at you, the frequency is higher, and when this siren moves away from you, the frequency is lower. So when the sun is moving away, the frequency is lower and the frequency is higher of light that you look at. Okay, so if you're looking at a faraway star, and here you are, so let's say this star is 100 million light years away, and if you want to know if this star has any planets at you, one of the ways of telling if a star has a has planets, you just look at the star, and if it's the frequency of light is changing, then the star is going in circles, meaning, and the only way it can go in circles is if it has planets around it, unless it has another star, but then you would be able to see the star. Okay. So that's one way of telling if a star has planets. Okay. Look for the light, observe the light of the star over a period of time, and let's say for 6 months its frequency is lower, and for 6 months if its frequency is higher, then that means it has planets. Okay. Did you guys understand that? All right. All right, so here is the center of mass of a system of particles. The center of mass is there. And to get the coordinates of the center of mass, the coordinate of the center of mass is the mass of each planet times its x-coordinate divided by the total mass. The y-coordinate of the center of mass is mass of each planet times the y-coordinate divided by the total mass, and so on. Okay, so that's how you find the center of mass. For a continuous object, here's the center of mass. And again, you can do the same thing, find the center of mass doing these integrals. Okay. Now, most of the time you will be interested in the center of mass of uniform objects, and the center of mass will be at the geometric center. Okay. So the center of mass of that object will be there. Yep.
Are we going to be finding the center of mass?
No, we'll just use tables. So again, but for most of the objects, we'll be finding the center of mass of uniform objects, and it'll be at the geometric center. And it'll be important for us because that's where the force of gravity acts effectively. Okay? Now, for an object like this, where do you think the center of mass is? It'll be somewhere here. Okay? Now, this is important because here's the deal. Okay. You guys know the sport high jump. Okay. So here's a bar looking at it from the side. You have an athlete come up here and then wants to jump across over the bar. Okay, now if an athlete jumps like this, what did he do? He lifted his center of mass from there to there. Okay, that's what he did. And essentially you have to do this much amount of work, mgh. Okay? And most athletes are roughly of equal skill. Okay? And most athletes can do the same amount of work. Now, on the other hand, let's say this athlete went over the bar like that. Now, where's the center of mass of the athlete? It's right there. Okay, so this athlete, by going over like that, his center of mass went underneath the bar. So he actually, he's capable of doing this much work, so he's actually capable of clearing this bar because he can go over like that. Remember, he is capable of lifting his center of mass up to that point. Okay? And this is called the Fosbury flop. Name it after Mr. Fosbury. He first did it in the Mexico Olympics. Okay, he was the first one to do it in the Olympics, and he won handily. Okay. And So you can watch this video of Mr. Fosbury. Okay, back in, everybody else was jumping over the bar like that, and he jumped over like this, and now everybody jumps like that. So he was able to clear a higher bar. Okay. Did you guys understand that? Yeah. I can show you the video, but I'll trust you. Do you guys want me to show the video, or you guys will go?
Doesn't show.
1968. The location was Mexico City. All was normal until a gangly 21-year-old civil engineering student in mismatched running shoes did this. That man's name was Dick Fosbury. And although it may not seem unusual to your eyes now, in 1968 it was revolutionary. On that day in Mexico City, the Olympic Games saw its first Fosbury flop. And it has rarely seen anything else ever since. The high jump has been a part of the Olympic Games since the beginning. Faster, higher, stronger. It's there in the motto.
You guys saw that? That thing is, I mean, your center of mass is so much higher than the bar. Okay, that is a very bad way to jump, but that's how people jumped back then. All right. All right. So the point is, it is useful to study physics. All right, so now, till now we talked about single particles, but now we'll talk about systems of particles. So let's say you have a bunch of particles, and this guy has a momentum like that. Okay. So the total momentum of the system is just the vector sum of all the momentum. Okay. And it turns out that the net force acting on the system is equal to rate of change of momenta of the system. Okay? So for instance, there is about 10 to the power of 28 gas molecules in this room. What is the total momentum of the gas molecules? The sum of momenta of all the gas molecules. Can you quickly tell me what is the total momentum of the gas in this room? I'm sorry? No, is the total gas going anywhere? No. No. So what is the total momentum of the gas? Zero. Okay, so you just added 10 to the power of 28 vectors quickly in your head. Okay? All right, so if you have a system of particles, so in this diagram, see, here's the system of particle, and there's the center of mass of the system. Okay, and now you can say something about the motion of the center of mass. It turns out that the net force on the system, so here are three forces acting on the system, and what the net force, the sum of those forces do is, here's the total mass of the system, give you the mass times the center of mass acceleration. Okay, so if the net force acting on the system is zero, the center of mass acceleration is zero. Okay, so no matter what crazy things they're doing, if the net force is zero, then this center of mass will move with a constant velocity. Okay, so let me show that to you, and that's actually kind of neat. Okay, we won't have a border, center of mass. Okay, so watch the center of mass. There's no external force acting on the system. We'll make it elastic collision. And watch the center of mass. Since there's no external force acting on the system, the center of mass will move with constant velocity before and after the collision. Okay. You see all kinds of crazy things can happen with the collisions, but the center of mass will not change velocity. And that'll be true for that pool ball when you break a rack. the center of mass of the entire system will move with a constant velocity. All right, now we'll apply this to rocket propulsion. Okay? Rocket propulsion employs the conservation of momentum principle. So here's a rocket. Okay. Now, when it was at rest, what was the total momentum of the rocket? So I'll draw this rocket again. This is at rest. Initial momentum was 0. Okay. So what we are doing is we are placing this rocket, let's say, on a frozen lake or whatever, or it could be you standing on a frozen lake with skates on. Okay. So your initial momentum is 0, and then what you do is you throw the physics book in your backpack in that direction. What should your total momentum be? Final momentum should be 0, so you would recoil in that direction. Okay? What if you want to speed up? I'm sorry?
You throw it harder.
No, throw another book. This time you throw the chemistry book. And so you'll go faster. You want to go faster, now you throw your calculus book. Yep. And that's the idea. Okay. So here's a rocket. If you want to go faster, you spit out some stuff. Okay. You want to keep going faster, you keep spitting out stuff. Okay. So when you throw an object in this direction, you're recoiling in that direction. Okay. What is the total momentum is remaining constant. Okay. What is the total momentum? The total momentum is the momentum of the rocket plus the of the momentum of the ejected gases. Okay. And that's the principle under which the rocket operates. Okay, so the operation of a rocket depends on the law of conservation of momentum. Okay, so for instance, so here's a situation. We'll consider this in deep space. So let's say here's a rocket. Right now its mass is that, and it's going at that velocity. So the momentum of this system is m plus delta m divided times v. Okay. Now what we're going to do is, of course, it wants to go faster. So what does it do? It spits out this amount of stuff in the backward direction. Okay. So the rocket goes a little faster. So now the momentum of this plus the momentum of this should equal the momentum of that. Okay. So that was the initial momentum. And the final momentum is, now the mass of the rocket is slightly less, but it's going slightly faster. There's the momentum of this rocket. And there's the momentum of the ejected gas. Okay. This much gas was ejected. That was the velocity. That was the velocity before. And then this was the velocity with which the gas was ejected. Okay. So this is the total momentum. All right, so if you do some algebra, this mass times the change in velocity is equal to the velocity with which the gas was ejected relative to this mass, and that's how much mass was ejected. Now the mass ejected is the decrease in mass of the rocket. The decrease in mass, that's negative, so that's why we have this negative sign. Negative times negative gives you positive. All right, so what is this equation telling you? This equation is telling you the mass of the rocket times change in velocity is equal to a negative of ejection velocity. That's the velocity which the gases are coming out, hot gases are coming out, times how much gas you ejected. Okay. Now you can integrate this equation. Okay, so this is in deep space. And the final velocity of the rocket minus initial velocity is the velocity with which you're ejecting the hot gases times log of initial mass times final mass. Why are these different, initial and final masses? If they were the same, that would be 1, log of 1 would be 0, and the final velocity would be the same as initial velocity. Why is the mass of the rocket changing? Because you're burning fuel and you're spitting out stuff. In fact, your final mass is probably about 10% of the initial mass. So this is about 9, okay? So if you want to have a greater final velocity, what is it that you need to do? Carry a lot of fuel and spit out the fuel very fast. So the greater the speed with which you spit out fuel, the greater your final velocity. Okay? So you look for rocket fuel where you can spit out the exhaust gases fast. Okay? So there's that equation again. Okay? And now we'll divide by T. Okay? Divide by dt. So the left-hand side is mdv by dt. What is this? mdv by dt. That is the thrust on the rocket. Okay, that's the mass times acceleration of the rocket. That's the force on the rocket. And that is equal to dm by dt. VE times dm by dt. What is dm by dt? That's the rate of change of the rocket mass. And what does that tell you? That's the rate at which you're burning fuel. Okay, so you want greater thrust, you have to burn fuel at a faster rate. Okay. When is the rocket the heaviest? When it's on the launch pad. That's when you need the greatest thrust. Okay, you need thrust greater than the weight of the rocket to lift off. Okay, and generally for rockets on the launch pad, the thrust is about 1.3 times the weight of the rocket. Okay. All right, so the burn rate is related to the thrust. Okay. Of course, we lift off from Earth, and so we have to take into effect the effect of gravity. And so the final velocity minus initial velocity is exhaust velocity times log of initial mass divided by final mass. And here's the effect of gravity minus g times the burn time. Okay. So for a rocket lifting off from the surface of the Earth, there's the velocity change is given by this equation. Okay. Again, this is in deep space. This is the thrust equation, okay, and this is with gravity in effect. Okay, so here are some numbers for the space shuttle that is now defunct. Okay, so when it was on the launch pad, it was heavy, so you needed these solid boosters. This is the main fuel tank that burned hydrogen, and so the boosters helped lift it up for the first 2 minutes. After the first 2 minutes, the boosters were ejected, and then the shuttle operated on the fuel contained in this orange tank. And then once this fuel was done, it had reached orbit. Okay. So it took about 8 minutes to get from here to orbit. Okay. And the orbital speed was 28,000 kilometers per hour. Okay. And this corresponded to an average acceleration of 1.5 Gs roughly. Okay. So here's the space shuttle, and the total initial mass of the shuttle, including payload, fuel plus tank, was about 2 million kgs. Okay. So obviously you needed a thrust greater than that to lift off. Okay. So the initial thrust was roughly 3.5 million kgs. Okay, so the thrust to weight ratio was roughly 1.7. Okay, so that lift-off thrust was quite large. Okay. The main exhaust velocities were 10,000 kilometers per second. Main engine exhaust velocity. These exhaust velocity of the gases coming out of here were 10,000 kilometers per second. And for each of the solid rocket booster, the solid rocket boosters burned 5,000 kilogram of propellant per second. Okay, so, and they operated for 2 minutes. So these guys were burning about 5 cars per second. 5 small cars per second. And the main engines were burning fuel at 12 cars per second. Okay. So a total fuel of 22,000 kgs of fuel was being burned per second for the first 2 minutes. Okay. So here that orange tank, liquid hydrogen was the fuel, and there's liquid oxygen, the oxidant, and there's the solid propellant. Okay. So maximum output, power output of the 3 space shuttle engines, main engines, was 40 million horsepower. Okay. These 3 main engines produced 40 million horsepower. Yeah. Equivalent to 20 Hoover dams. Yep.
How much does efficiency take into play for this?
I'm sorry?
How much does like the fuel efficiency take into play? Because like obviously like all the fuel that's being burnt up, not all of the energy is going into.
Yeah, so this is a heat engine. Most heat engines have efficiencies, well, they depend on the temperature, efficiencies about 40%, 30%. Mm. There's the space shuttle. Its thrust was 31 million newtons. The Starship is twice as powerful. The Starship will be more powerful than any rocket built. Yeah. And of course, Elon is using this to launch 50 to 100 satellites, Starlink satellites per launch, and that's the idea. Yep. Yep. All right, guys, so that's momentum.